I will give a very intuitive explanation of how AI generates images based on text prompt. You don't need to have any background or any knowledge in AI, and you will understand completely and very intuitively how the AI generates images from a text description. It's gonna be focused on how Stable Diffusion works intuitively, and this way of thinking about this was created by Jeremy Howard. Now let's say we have some magic AI model. This is a magic, like a black box. It doesn't matter how this works. And we have some picture of a handwritten digit. Let's say we call this x1. We put this through our AI model, and our AI model spits the probability of x1 being a handwritten digit. Well, in this case, let's say probability is 0.97. It goes from 0 to 1, the probability. Now let's say we have a bit different picture. Let's say we have something like kinda like this. It kinda looks like 3. So we put this into our AI model, and it spits the probability of x2 being a handwritten digit, let's say 0.56, and this is x2. And let's say we have some random noise example. This is nothing written here, so the probability of this being a handwritten digit, probability of x3 being a handwritten digit, let's say 0.01. Now, what's very interesting is we can use this AI model to generate pictures of these digits. Let's say this picture here is 28 times 28. If we, for example, change this pixel, make it dark, what's gonna happen with probability of this being a handwritten digit? You see that it kind of reminds of a number 8, so the probability is, let's say, gonna increase to 0.07. Okay, and let's say I also make this pixel, random pixel, darker. Now, digits usually don't have dark pixels in the corners, so the probability of this being a handwritten digit is gonna be reduced to 0.0, let's say 5. This is how you can use this AI model that's called classifier to generate pictures of handwritten digits. If you prefer learning in a group, check out the link below where we have our courses and our teachers who are going to help you learn, where we have not only the video lessons but also community where you can ask questions, make posts, comments, etc. And we are all helping each other learn machine learning, research, and engineering. I'm going to be very active in the community, and I'm going to answer all of your questions, and I'm going to make lessons that you request, and I'm going to teach things that my students request. New course lessons are coming daily. We have Stable Diffusion text-to-image web scraping, large language models like GPT, Llama 2, etc. Then beginner, intermediate, advanced courses. All of this is included in a single monthly membership, and you have the community, the comments, and everybody trying to help each other, and us teachers trying to help you become AI researcher or engineer. So if you want to generate pictures of handwritten digits, you can have basically two models, generator or diffuser, that's going to change the values of pixels, and the discriminator or classifier, who's gonna measure the probability of that new image being a handwritten digit. And the diffuser is going to learn what kind of change in pixel color on these images is gonna lead to the greater probability of this being a handwritten digit. From this, it's only important that you remember this word classifier. Next, we are going to talk about how this classifier works and how we can make it. Now, let's say we have a few pictures of a few digits. Let's say we add a little bit of noise, random noise to each image. So let's say I'm gonna add just a little bit noise here, a bit more noise to this image, and then I'm gonna add a lot more noise to this image. If we look at these images, we can see that this image is basically equal to this image of a 3 plus this noise that we added. And then we can see that this image is equal to this image of a number 7 plus this noise that we added. And same for the last image. It's equal to this image of a number 8 plus this noise that we added. Now let's say we have some neural network, magic neural network black box AI model. It doesn't matter how it works. First, how do we actually put these images into the AI? Do we put kind of color values? Do we put, what do we, like, how does AI actually take these images in? Well, as I said, each image is a 28 by 28 pixel grid. Let's say this is 28 by 28 pixel grid. This is color black. This is color black, color black, color black. Like, let's say this is number 7. So these are all color black. And then these pixels, other pixels are white. So we can just say white pixels have value of 0. Black pixels have value of 1. And now we can very simply pass this image into our AI model. We can just make an array, and the array will go like, for example, this side. So it's going to be 0, 0, 0, 0, 0, and then here 0, 1, 1, 1, 1, 0, etc. So we're going to have 0, 0, 0, 0, 1, etc. So if we are passing this image into the AI, this is going to be our input. And then the values are going to be 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. Now this is very interesting. We can actually train it to separate it into this number and this noise. But we don't need to separate it in both. We can just ask it to predict this noise. And once it has predicted this noise, we can just subtract this noise from this image, and we can get this number. Now, why would we ask it to predict the noise? Why don't we just tell it to predict this number? Because we want to be able to give it a purely noised image later, completely random noise, and ask it to predict the noise so we can subtract the noise. So let's say it predicts some noise, and we subtract the noise and we get number 3. This is how we can generate a non-existing image of a number 3 from pure noise. Let's say we want to generate a picture of oil painting of an otter in a top hat. This is what Stable Diffusion would do. On the left side, you can see the noise. It starts from the random noise. On the right side, you see the subtracted noise that is currently subtracted. So in the beginning, let's just look at the left side. It starts with random noise. Then you can see that it's predicting the noise and it's subtracting it such that this picture of otter is forming. And it's predicting noise in multiple steps. It doesn't predict it all of a sudden, but it predicts it in 100 steps, 100 times. And it's subtracting the noise, as you can see. And then as it's subtracting the noise, we get the image of the otter. On the right side, you can see completely removed noise that is predicted. Now, obviously, it looks bad because it cannot predict the complete noise in the first try. That's why we do multiple tries, so it's going to predict more and more noise step by step. The way we train this model to predict the noise is we actually take a bunch of these images and then we add noise to them randomly. We can add 0 noise, we can make it completely noisy. And then we ask it to predict. After the noise, after we ask it to predict, let's say it, for example, took this image and predicted the noise to be like completely different. Then we compare this noise and the actual noise. And then we adjust a little bit the model so that next time it's going to be closer to this instead of this. So this model right here, this is called unet. The input to unet is noisy image. It can be a bit noisy, like it can have 0 noise or completely noisy or anywhere in between, and the output is the noise. Such that if we subtract this noise from this noisy image input, we're gonna get our image without the noise that we are trying to generate. Now, in the real world, the situation is a bit different. We have images often that are 500 pixels long, 512 pixels high, and 3 channels deep. So red, green, blue. Each pixel has the amount of red, the amount of green, and the amount of blue color. So when we multiply all of this, we get that we have actually 786,000 numbers for each image. Now this information is basically contains the entire image, so we need to pass this into our AI model. Now this is actually too much data. There is a way to reduce this number, to reduce it, like divide it by 48, like reduce it 48 times. And then this a lot smaller number we can pass to our AI, so it's going to be a lot more efficient. And this image, this is the same representation of this image. Now it's going to lose actually some data, because this is the perfect data of the image, but this is going to lose some data, but only minimal amount of data while being 48 times smaller. And this is how we are going to do this. So let's say we have our image, and we are going to pass this through something called stride 2 convolution. It doesn't matter what it means right now, but I will explain just what it does, and I will explain how it works later. So when we pass this image through stride 2 convolution, we're gonna get 256 times 256 times 6 channels deep. Now, if you multiply these three numbers, you're gonna see that there is less numbers than when you multiply these three numbers. So actually, some data is lost, but I will show it's only a bit of data that's lost. So we can see this is the width, this is the height. But what does this 6 mean? Is this like 6 colors? Because this was red, green, blue. Is this like 6 colors? No. This is actually another dimension of these numbers, and we don't actually know what those numbers mean. They might mean some kind of colors, they might mean something, but imagine this whole thing as containing compressed data of this thing. And we don't know exactly like what each of these numbers mean. They do not correspond, like this pixel does not correspond necessarily to this pixel at the same position, the same coordinate. It doesn't. It just imagine this as some magical kind of data that closely represents this image but with less size. And now we will pass it again through a stride 2 convolution, and now it's going to be 128 times 128, and it's going to be 12 in the depth. We don't know what these numbers are going to represent for now. We can know in a specific case-by-case situation, but we don't know, like in this general case, there is no general rule what this 12 in the mean, like what it represents. And let's say we pass this again through a stride 2, so we get 64 by 64 by 24 in the depth. And now this is going to be the smallest model, but it closely represents this big thing, but a lot smaller. And let's also pass this through a ResNet model. It doesn't matter what it is for now, but this is just going to reduce the number of this 24, that should be 24 into, for example, 4. So it's going to be 64 by 64 by 4. This is called ResNet. Now when you multiply this ResNet model, you're going to see that 64 times 64 times 4, you're going to get only 16,000 pixels here, which is 48 times smaller than these 780,000 pixels we had in the beginning. And the main thing is that this actually contains almost all of the, or very accurate data that this contains. Now, after we have this compressed version of the image, this whole thing is called encoder. It's going to encode this original image into this latent, this is called latent image. But we also need a decoder. We need the exact decoder that's going to convert this latent into the original image. So let's say somebody sends us this latent image. We actually need a copy. We need a decoder. This is going to convert this back to 64. As you can see, we completely reversed this process, and we got back to 512 times 3 to the original size. Now, you should know that during this compression, some data is actually lost, although minimal amount of data. So when you convert it back into this original image, it's going to be a bit different than this image. So maybe if you have a bunch of leaves, the leaves are going to be a bit moved, a bit different shape, a bit different color, but it's going to be like very small details that are going to be a bit different. What we have just created is a very powerful compression algorithm. We're going to convert this big image into a very close representation that's 48 times smaller, and then we can train our AI with these 48 times smaller latent images. So what we would do is we would get a bunch of images, we will convert all of them into latent images, then we would actually train our AI to generate these latent images from noise, from text encoders, and then once we generate these kind of images with the AI, we're just going to pass them through this exact same decoder, and then we're going to generate the big image. Now this whole thing, this can be considered an AI model, and it's called autoencoder. And it's important that this whole thing is trained by itself. And what it's trained to do is compress a big image into a small latent, and then compress it, and then expand it back into the big image. The way you would train this is you take this image, you compress it into the latent, and then once it generates back the big image, you calculate the difference between this generated image and this image. And then you update the AI, like you update the AI that's generating all of these like steps. So this image is gonna be closer and closer to this image as it trains. Now let's just draw with the red lines like this this is our AI, and inside of this AI we have this autoencoder. Now in the beginning the AI is gonna compress this randomly, and you can imagine that when we go through the whole process, this is actually going to be complete random pure noise when the AI is not trained. There is literally zero data. It's completely different from this image. That's an actual image. But as we calculate the difference between this image and this image, which we also call loss is the difference, we're going to update our AI. So this generated version at the output is more and more similar to the input images over time. And now we understand how we can train our AI to generate completely new images. So first, we're going to get a bunch of images. We're going to compress them down to a latent image. Then we're going to feed all of these latent images into our unet. Unet is going to learn to generate these proper latent images. And then these latent images are going to get decoded by the decoder into the big images.